Hi, and welcome to our Offensive Tool Development course. I'm Christopher, and I will be the instructor for this course. Throughout this course, we do have dedicated discussions and community pages for this course that you can add questions in as you go through and things like that. But you can also reach me via email listed on the slide here as well, whichever works best. But I do generally prefer the discussion and community format so that we can all kind of engage in whatever it is you have to ask about the course or content or your own related work. Now, as we kind of jump into this, the purpose of this kind of introductory slides here is really to set expectations, to demonstrate the things that we'll cover. Now, this will be not a completely exhaustive list, but it'll cover the main things that we will be, talking about, coding, our projects, and things like that. Now, the nature of these courses is that I tend to extend them, modify them, add content and that over time, so that year by year, or even month by month sometimes, it can it can evolve based on the evolving landscape of the materials themselves, and also client requests, student requests, things that people are perhaps struggling with. I like to be able to explore them with everyone and kind of enlighten whatever their struggles are. Which is why you'll see in this, some of the things that we'll cover may not be the very common things that you see in public. Now, we will touch on those, and shortly I'll actually be diving into more about what we will be looking at and working on compared to some of the other things out there that we don't really touch on much. But even the things that we don't touch on much, I generally will still mention and talk about. But I'm really here to focus on the harder concepts, the things that, from my personal experience and from discussions with others in the community, the things that tend to be the most difficult to understand or work with, or that are the biggest limitations in advancing either someone's red team operations or their own tool development type thing. Because we tend to get, from what I notice, is there is a lot of red teaming out there. And I say red teaming when this is about offensive tool development, just because a lot of the users of this course are going to be red teamers, but not everyone. But there is, from my experience, especially in certain regions, a lot of teaming is not very bespoke, or rather there's limitations on one's understanding of the tooling and of the defensive landscape and things like that can come into play, which it does make sense because there are so many different skill sets that go into this. When you look at how certain APTs operate, which we will be later as well, there's generally a separation or segregation type thing between operators and developers and reverse engineers and vulnerability researchers, or just zero-day acquisitions if they're just paying for it. And that generally requires a lot of, team members in the first place with a certain set of skills. And then, you need a budget for that as well. I'm not expecting red teamers here to have multi-million-dollar budgets to go and spend on a 0-day to pop a client or something like that. But which is why throughout this course, we'll be going through the different levels of, I guess, effort, but also financial effort or financial funding and capabilities and stuff to achieve the same thing. For example, one actor might be willing to spend $2 million plus on a RC or LPE or something for their target, and then leverage that in their red team operations. Someone else may not have that funds, but they may have the team members and skills required to find those vulnerabilities, which is another approach that we'll touch on and we'll actually leverage ourselves. And then there's the other side of it where you're very limited. You have limited time, perhaps even limited skill set or limited effort you're willing to put in on this job. This mostly relates to actually red teams in legit areas where you're generally doing red team client to client, and sometimes you have 3 months, sometimes 6 months, sometimes a year, sometimes even shorter. But even with those limitations, there are still some very fast ways to find 0 days, especially in like logic bugs in software that your client runs, that you can actually leverage that on your red team, which is an approach that I've taken in the past multiple times. When I used to work internally on red teams for like big banks and stuff, where you can spend, like I've spent no more than 2 days to find the software that runs on a client PC, install it in my own lab, and find a privilege escalation 0 day in it, weaponize it, and use that on the red team properly in like less than 2 days. So there are definitely those types of bugs that are very feasible to kind of find and exploit very quickly. And we'll be going through those as well, because that kind of plays into our tool set. So some of the other things we'll be talking about, that kind of fits in, I guess, methodology from a high level, right? Where we can talk about the different steps that generally occur in a offensive campaign and how that relates to what we'll be learning. Now, before we kind of jump into tooling and that, or even throughout tooling, we'll always be kind of coming back to hardware and hardware knowledge, because our tooling, right, it's software where, in this course, I'm not really working with hardware level implants. So we're not going to be like creating or soldering custom, malicious USBs and things like that. We'll be working solely in the realm of software. Well, not 100% solely, right? Because our software very much runs on hardware, and sometimes we need to keep that in mind. Now, when you're writing userland stuff, right? Like you're writing, a C userland binary or something like that, sometimes hardware doesn't matter as much. Like a lot of that is abstracted away from your coding. If you want to write a program to read a file and then send that data over the network, you don't really have to know hardware to do that. You just need to know the APIs to use on the operating system you're expecting to run on. Now, if you're writing this in the kernel, that's a bit different. You will need to know some hardware usually. And if you're leveraging your own hypervisor implementation, that's going to very much so be interacting with core hardware CPU features and MMUs and extended registers of CPUs and things like that, you will need to know hardware. And sometimes, depending on what you're doing in user, you'll also, you can benefit from knowing how hardware works by knowing how page tables are set up so that you can manage your shared memory and shared memory protections better and understand what's going on. The main point here is that CPU and hardware is very much entwined with the kind of tooling that we'll be writing. So we'll have an initial kind of batch of prerequisite knowledge we'll have to understand. And then there'll be more that comes out of, as we go through. For example, when we get to hypervisor and kernel section, there'll be more. Just because of the nature of the fact that we are going to be interacting with a lot of these hardware, even directly, completely disregarding any OS APIs and things like that. Then we'll be examining some existing tooling, both public and private. So, this public relates to, papers and GitHub repos and research from the community. Private is both malware, which may not be documented very well. So I'll provide some samples and we'll actually do a little bit of reverse engineering to extract some of these techniques. And this is a useful skill to have. Both in the sense of being able to understand and extract hints from public like APT reports, but also being able to reverse and find interesting techniques in malware themselves by doing our own reverse engineering of it. And also this will extend to reverse engineering certain components of the operating system to find undocumented behaviors that we can leverage in our tooling. without needing someone else to have found them first and posted it online for us, right? We can find it ourselves entirely. And private tooling also includes commercial tools. So, frameworks that you pay for. Think like Cobalt Strike, for example. What was the other one? Like Nighthawk or something, right? Brute Raytail, or however you pronounce it, C2. There's a few commercial C2 frameworks out there, and we're going to examine them based on, as legit and legally as we can, based on what's publicly out there on those tools already, which we can actually infer based on some of the features that they list as well. We want to be able to see a feature listed on its website or something, or by some report, and then be able to figure out and implement that feature ourselves with as minimal information as possible. And we can do that, or we'll have a higher success rate of that if we have good working knowledge of hardware and software, which will come into play. And then we'll examine some advanced, less common techniques, including techniques that aren't mentioned really in public or private, techniques that I myself have come across or have thought about, or that we even together can think about and work through, or just techniques that people know exist, but there's not really much offering for them. Things like custom boot kits, custom root kits, blue pill hypervisors, and things like that, where there's either very little to no really useful public research on it, or there are, but they're more like proof of concept type things. And our tooling that we're going to be working on primarily relates to things that we want to run in production, or on target machines and things like that, which means it's got to be more than a proof of concept. It has to be pretty complete. It has to be stable. It has to have logging. It has to have ways for us to detect bugs and proper error handling. It's very much got to be productionized for our users and not a proof of concept. That said, some techniques that I will go through will be purely proof of concept for a variety of reasons. Some of them are very, development heavy. So we're going to take kind of two approaches here. Maybe it'll be best if I kind of switch up the screen a bit and work through these. So one approach is writing production ready code. Writing production ready code. Okay. This is some of the code. Some of the code that we'll be developing will fall into this bucket. And by production ready, I mean things like, it's stable, it has error handling, it has logging, it has documentation, it has, Okay, it has documentation. What else? Few other things, right? Maybe it's extensible, blah, blah, blah. But the main point here you understand is that this is quality. This has been tested. It's stable. It's not going to blue screen or crash things randomly. It's got documentation, which I will say is a very key point here. Everything that we write for our production ready code will be documented heavily. Heads up, we'll be using a lot of Rust. So Rust has a nice method of turning comments into documentation with Rust docs. And you can even link things to each other. So it gives you like a, maybe this would be a good example. Rust doc example or something. Doc.rust.lang, I think, follows it. Or maybe I should do cargo doc example. Okay, let's see if there's just trying to see. I'm not sure if this is actually compiled in cargo doc. It very well could be. but what I really want to find is just an easy thing for me to browse. And demonstrate. So for example, this is how it looks like in code, right? 3 slashes, you can document structures themselves, variables or parameters to structures and to functions. You can use links to, link parameters to certain types, and then you click that parameter and it'll take you to like the type or the structure of it. There's lots of different attributes for the documentation. It's quite nice. It's what's used to generate this documentation. So this documentation here is built with Cargo Docs. You can see that we have like links and stuff. If you click something, shows the module name. Here it even links it to the source, which is quite nice because you can just view the source for any function you want. It shows the structs that are used and you can click them and it links it to the struct documentation. And it's a very nice way of viewing docs. And we'll make sure that we have documentation for our production ready code. We'll have logging, error handling, it'll be extensible. There'll be lots of other things that'll go into it to making it quality. And from personal experience, this can actually be harder than writing the techniques themselves sometimes, sticking to, very quality code. But it's important for a number of reasons. One, there may be some scenarios where you may think it's not as important. Usually that's where you have like a one-man red team almost, or like one person writing out code and using it and just kind of going through techniques and stuff like that. But we want to make sure we cover scenarios where there's multi-person teams where multiple people could be developing on the same code base or the same framework, or even where you have separation of developers and operators. So in that case, the developer would want key documentation to pass on to the operator who's actually going to be running the code on, target machines. And then we'll have the other bucket, which would be like, box, proof of concept type things that really focus on just implementing the technique. So focus on technique, not quality, I guess. And the reason for this can be multiple. There can be multiple reasons here. The common one is that it is very time intensive. So what I mean by that is we have some sections where we'll be writing custom hypervisors like from scratch. Now, there's a couple approaches that I have in mind for when we get to there, and it'll likely be split up into a couple different areas. There's the part where we code it together. We work on it together. I give you challenges and, I'll walk through the answers and give hints and things like that. For some of the very time-intensive techniques, some of these may be focused around proof of concepts, where I want to make sure that you as, the student here understands the technique, understands how to create the technique, how to code it up, can work with it and things like that. And you're not focused on stuff that you can do in your own time, like documenting it, making it stable, adding in error handling, things like that, right? Because if you get to the point where you understand everything involved and you've done the hard part of, implementing the technique, even very kind of like alpha-ish, but you've done that and you understand the hard parts, then I want to make sure that all that remains are the easy parts that you can do in your own time outside of this course, or, with assistance from myself, because I'm always open to discussions and questions and things like that. But as long as you understand kind of the challenging parts of it and you've actually done it, we have implemented the technique or, techniques required for it, then you can go off and continue that development in your own time. Now, something I want to stress here is that I'm not saying that you're not going to learn the techniques, right? You are definitely 100% learning it and implementing it alongside me in this course. But there'll be times where there'll be repetitive things. Usually the time-intensive ones are repetitive. So what I mean here is, say, for some of our techniques, we need to do something. That something can be, I'm going to say do something here, but that could be multiple things. It could be something as simple as, writing a custom, writing a manual syscall implementation, something like taking NT read file and implementing it yourself instead of using kernel's read files or using NT's read files, implementing that API yourself, doing the necessary syscalls yourself, or even doing things like taking load library and implementing it yourself. So in this case, right, instead of using load library to load a DLL into your process space, maybe you write your own custom loader that can take the file bytes and map it into your process space yourself, even do things like linking it into the PEB and pretty much like everything that load library can do, but you're doing it completely yourself in your own code, fully documented, not in partially undocumented, unexported functions that live in NTDLL or kernel base and things like that, right? Now, sometimes the approach is what's unique here. So such that if we practice taking multiple, say I say take load library and implement it yourself, and then the next task is like do the same for, I don't know, what's another kernel function that would be useful to implement yourself? Maybe, I don't know, unload library or something, right? Where you're like unmapping it from your process space, taking it out of the PEB, stuff like that, right? Now, generally, the only unique things between these two tasks is learning how to do it in the first place, such that if you can do one, then doing the other is not difficult at all. In fact, it's extremely easy. So in this case, there's only two. But what if there were like 10 or 15 tasks that were very, very similar and needed to all be done, but they all relied on the same skill base? In which case, we may focus on one or two to make sure you've understand how to do it and you've actually done it yourself as well or alongside me, and we understand everything involved. And then the remaining, 8 that leverage the same skill sets, you can do, say, in your own time. Or I can provide a completed solution for, and based on the fact that through our challenges, you've implemented 2 of them, and I provide the solution to the rest, you can then explore the rest in your own time by referring to my solution and the 2 that we did together. Things like that. Now, this is solely to kind of save time because this course is already very content heavy. We'll be covering so many things in here that I don't want the course to be like a 1-year long task. This isn't a bachelor degree or something. So I'm striking a balance here. That said, if I miss something or there's extra content that someone wants me to walk through or you yourself want me to walk through, please let me know. Send me an email, send me a message, add it to the discussions, because anything that I see that I may have missed or that people want me to focus on more, I will extend the course with that content. I do that already for my existing courses, and this one is no different. So that's definitely there. But I'll be sure to also take care in making sure that we implement the techniques, we do the work for everything that we walk through, such that anything that I kind of skim over or give the complete solution to without having an associated challenge for it, are things that I already know we can do because we've already done it in, in like a proof of concept manner. And the remaining work is just maybe adding documentation or polishing it up with error handling, which I will also cover. And then it's just a matter of, your own time investment into that. And this also leads into the different type of people or kind of goals that you may have when taking this course. And there's kind of three, right? Or at least there's three that come to my mind. One is you want to write your own framework from scratch, right? This means that you're writing things that pretty much compete with, Cobalt Strike. They compete with Nighthawk C2 or whatever it is, with APT C2 frameworks and things like that. You want to write your own framework from scratch. You don't want to use Cobalt Strike or Nighthawk or whatever, or maybe you are, but you just want an alternative to them. You don't want to pay their licensing no more, or you want something that you have full understanding and control of. Now, this is a heavy lift, right? Depending on how many features and things you're expecting to add into them. And, in this course, you'll learn how to write your framework from scratch. We will write a framework, actually. But because, this isn't me giving you a complete private, I'm not creating and giving you a full custom Cobalt Strike implementation with everything it has, right? Because the development time that can go into that can be pretty high to cover every single thing. But we will have a lot. And with the learnings that you take from this course, you can then put in the extra time to convert that into your own framework from scratch. You can take the pieces that we create, the initial framework we create, the techniques and code that we work with here, which, like I said, focuses a lot on the hard things, on hypervisors, on kernel rootkits, on bootkits, on advanced user techniques. You can take our implementations that we create in this course and then continue with whatever's missing or whatever else you want to add into your own framework from scratch. That's one group of motivations or students that will be taking this course. And there's a second. The second is extending, right? Extending frameworks. This is where you already have a framework, whether it's a in-house custom framework or something pulled and modified from an APT, or a commercial framework like Cobalt Strike or Nighthawk, or even a public one like Covenant or whatever else is out there in the public, Metasploit and things like that, right? And this is where you have those tools. And a lot of these tools allow you to provide your own modules, your own custom tools as well. And you want to extend them. Say these tools, have techniques that you find are being detected too easily, or they just don't have certain techniques at all. Maybe none of them include a blue pill hypervisor module. Or perhaps you want to write your own custom loader and not the custom loader included in these frameworks. Perhaps because you're operating on, target machines that have EDRs specifically tuned to detect the loader from whatever framework it's using. Maybe they have very good detections against loaders that are included in Cobalt Strike. So you want to provide your own version of that loader, right? That's the other second bucket that a lot of students will fall in. And that's also covered by here, of course, where we can create modules and that leverage techniques that we want that can also be packaged up as a kind of individual thing and leveraged in a existing framework. So that's kind of the main two here, right? Where you create your own framework or your extending framework. There is kind of a miscellaneous other few that include things like just using individual techniques as standalone tools. Perhaps, you have a loader or something like that, and you want to use that as a standalone tool outside of a framework for whatever reason, or there's some other use for it. But the main point here is that we'll be covering both of these approaches. We'll be exploring both of these approaches. when it comes to extending frameworks, I'm not using any commercial ones in my course. So a lot of our tools, I can show how they can fit into public ones like Covenant or other GitHub ones that we'll take a look at. But once we explore how to leverage our module in a public one, it's pretty much the same leveraging it in a private one. They all have support for that usually. So that's fine. And writing your own from scratch, we will start our own framework from scratch as well to kind of explore this. And then if you like to continue development on that in your own time after this course, I want to make sure that you have the skills and the experience to be able to do that with minimal effort, right? Okay. Cool. And so, part of what to expect, like I said, we'll be kind of leveraging a lot of custom implementation of techniques. And the custom implementation will focus a lot on Rust. So we're going to be using a lot of Rust code in this course. Now, there will be some C code, mainly when we get into some kernel stuff, but they'll mostly be stubs, like C stubs that can work with the OS to then call into our Rust code to handle most of it. But we'll also be, considering strategic design, secure coding, our framework development and design as a whole, as well as we look into these our code. We're not just writing techniques. Like I said, some of it is going to be very much so production ready. We need to keep in mind other design level things of our code before we kind of just start hacking away in it. We'll be covering a lot of low-level techniques, so like rootkits, hypervisor development, bootkits, even userland stuff can get pretty low level as we start considering how page tables work, how the hardware operates, interrupts, page faults, and how we can kind of abstract control flow via exceptions and interrupts and the differences between those different interrupts, and where code execution can go with things like structured exception handling and things like that. We'll also look into anti-analysis and anti-debugging, things like using custom encryption, custom packing, virtual machine abstractions in our code, modular designs, things like that, because, as I kind of mentioned, the trade-off between time and development earlier, we'll be exploring in some cases, multiple approaches to the same thing, where both approaches give you stealth, they give you the ability to hide your code and things like that, but one may be way more resource or time intensive than the other. So then, for example, writing code that's easily detected, but then leveraging custom packing routines to obfuscate the final result so that your development time into that code is pretty fast because you're just using normal Windows APIs. You're not doing anything stealthy. You're using regular development resources that allow you to develop code fast. And then to handle the stealth part, you're using your own custom packing and encryption routines to hide it after it's being compiled so that you have relatively fast dev time, but you still get stealth by using your custom packing versus, coding from the start with stealth in mind, not using the Windows APIs, but using your own custom implementation of the APIs you'll be leveraging, custom syscalls or inline syscalls or things like that to avoid API detection, including passing the PEB to extract exported functions instead of using imports or using getproc address. So you don't even have getproc address as an import into your program. You're implementing getproc address yourself by passing the PEB, finding the DLL, or manually loading it if it's not there, passing its export table, finding its the function pointer, and then calling it directly, right? In that case, you don't need custom packing really because your code's already obfuscated and stealthy, but your development time may be higher because you can't just use the Windows APIs. They're both approaches to the similar goals, which is stealthy operation of your tools. And they both have their own pros and cons and different potential detection points and things like that. So we'll be exploring both approaches to some of the tools we work with. As mentioned, understanding of techniques, private researcher code, APT, We also need to analyze and understand the detections and defensive tools that we'll be coming up against: EDRs, XDRs, AVs, logging tools, even just ETW logs, was it Sysmon and things like that, so that when we think about stealth, we are aware of the tooling that we'll be going up against, its techniques, and how we can kind of approach that. And we'll be figuring that out based on a variety of methods, both via just public research on it, but we'll also learn how to reverse engineer EDRs and AVs to identify some of their techniques ourselves. This comes in very handy where you may have licenses to an EDR or something because, you're an in-house red team for a bank or something. And, the best way to then learn about its detections is to just reverse engineer it. Or, you may be able to read its documentation and stuff, but I find looking at the code itself gives you the answers. So we'll make sure we practice reversing some of these things and identifying their techniques. And then writing and designing bypasses. And like I said, there'll be core knowledge that we'll have to cover as well. Some of the core knowledge relates to the boot environment. So the different modes a CPU can be in: devices, page tables, ACP, bootloaders, firmware, secure boot, and how that affects the operation of the OS. Then we have like the system environment. So, privilege separation concepts, CPU extensions with extended registers, virtualization, certain, Intel or AMD specific things like SGX or SEV-SMP, interrupt handling, the associated software like kernels, hypervisors, HAL, drivers, all of that stuff. Quick note, we are focused on x86 64 Windows primarily. That said, we will actually be working with some code that we will be able to easily cross-compile to ARM. And I might have some sections that actually do run our code that runs on x86, also on ARM64 Windows, leveraging cross-compilation capabilities of Rust. I may extend this to macOS down the line, but in its current state, it's focused primarily on Windows. And then, we're going to learn about the operating environment. So the different CPLs, MSRs, how traps and faults are handled and how we can leverage them in our own code, as well as certain software concepts that we'll be working a lot with, like the PE32 and 32 plus formats, the COF format, what is a process, how scheduling works on Windows, the different interfaces with the OS via core DLLs like NTDLL, kernel 32, GDI for like the underlying graphics subsystem, and all these different things that will come into play with certain techniques that we'll be using. When it comes to understanding the techniques, as mentioned, there's quite a few APT and malware techniques and public researcher code that we will look at for a variety of reasons. On the APT and malware side, a lot of them have been used successfully in real campaigns. And, so that makes it really a prime target to analyze because we're generally using our tools for our own campaigns. So analyzing successful ones can influence our own designs. Sometimes they also include cool techniques, right? And, for some red team frameworks like CBEST, Cori, and similar frameworks, they generally have requirements to mimic the real tactics and techniques of existing threats. So being able to analyze and implement those threats ourselves kind of satisfies that as well. Then we have public and researcher code, which isn't necessarily distinct from malware APT, but can be. The biggest risk here is copy-pasting public code, right? Which even APTs do, and potentially even commercial tooling. And some of them are known and commonly used, yet still effective. Now, with our own implementations of these techniques, both public and APT malware, I have a kind of strict policy here that we're not going to be copy-pasting any implementations of the code we look at. We will understand the design, understand the purpose of it, and how it may do things, and we will also identify potential improvements, features, or risks of it, and we'll implement it ourselves. Some things we may be able to go completely different implementations than what we see in existing code, but has the same kind of design or purpose. Some of them are techniques that, don't have such a variety of ways of being implemented, but we will still implement it ourselves in our own framework with our own documentation, not relying on copy pasting or the implementation of existing code, just the design of it, the key points of it, enough understanding of it for us to implement it ourselves. That said, I'm not against copy pasting certain things in your own tooling or, in your own work, but for the purpose of this course, we were focusing entirely on no copy pasting, just implementing things ourselves. Also, we're working primarily in Rust, and a lot of the code we're looking at probably isn't going to be Rust-based, so we'll have to do the porting, really. Or not really porting, because we're writing it ourselves, but you won't be able to copy-paste, because we're going to focus on Rust. With EDRs and EVs, there's certain different methods of detection logic, right? You've got passive level stuff, which is the correlation of logs from, ETW, canaries, things like that, artifacts on file systems and network traffic. And then you've also got active things where they look for differentiations from baselines or different patterns, behaviors of a tool. If there's some processes that's been baselined on a system, and then suddenly it's talking to some DNS host that it's never talked to in the 100 plus days that the EDR has been running on that system. That's a baseline differentiation. That's a different pattern or something that goes against the pattern of behavior previously identified, which could mean that perhaps some code has been injected or modified into that process to do something else. You've also got the binary structure and runtime analysis things when they run your code in a sandbox to detect malicious patterns and things like that will be making sure that we understand kind of all these different ways that it collects information, and then the detection logic that it uses to identify threats. So we can keep that in mind with our own code. Part of the methodology, we're going to be looking at typical red team playbook, where you have the kind of process of the simulation on the left-hand side. You got your recon, your initial compromise, lateral movement, and then achieving your objectives, right? So you're pretty much getting into the target network, hopping around to wherever your goals, wherever you need to be to achieve your objective, whatever that is, whether it is, extracting funds from a bank or ransomwaring the whole thing to bankrupt someone. Every kind of APT or threat has its own objectives. And then to achieve that, you have supporting techniques, right? You have tools for privilege escalation, persistence if required, reconnaissance, detection evasion, all that sort of thing. Then we have similar kind of example infrastructures where you have a target machine, right? And you deliver a payload to that target machine. Generally, you have your own machine that connects to your server where you launch, attacks from, or that maintains, the logs and everything from your C2. But that server doesn't directly interact with the target machine. It may go through VPNs. It may go through a cloud machine, or even a compromised server that pretty much acts as a tunnel between your actual attacking server and the target. The purpose of that is so that you hide your actual server that contains your logs and your Xfield content from the target, so that the actual server that delivers payloads to the target is just a tunnel. It's a cloud machine, it's a compromised server, it's something like that. You also have ways here where the target machine, once it's running the C2, may request modules from your server, privilege escalation modules, reconnaissance modules, things like that. You can also do some pretty cool things that we'll look into, if it requests modules outside of certain times or multiple times instead of just once, we assume that it's been compromised and it's being run by defenders to analyze its behavior, and we can serve dummy data or do certain other things to kind of hide what it really does. We got to think about operational concerns. Accounting is a big one. The logging of all operations taken on targets. This also includes, leaked artifacts, which can be things left in memory, in disk. One thing that also commonly gets, missed are things that get added to cache, right? If you send an email to someone and there's, a picture in it, and that picture maybe contains obfuscated malware embedded in it, that may be cached to disk somewhere outside of even the email itself. So caching and artifacts from that are also things that we need to try and keep track of as well, so that at the end of our operation, our framework or whatever we're working with can easily identify the operations that we took on our targets and also any artifacts that were there, so that we can do cleanup after the fact. This is very important when doing, legitimate work. Well, actually, it's important in both senses, right? For legitimate work, red teams internally and things like that, you don't want to leave backdoors or malware artifacts on your client machines. Likewise, if they ask, what did you do on a certain machine, because maybe during your red team operation, something went wrong on their side and their servers went down and they're looking for someone to blame, you can show them the operations that you took on the targets and whether they led to it or whether they did not lead to it. Because there's been cases that I've seen where if something goes wrong on a client side, even if it wasn't your fault, if you can't prove it wasn't your fault, they may try to pin the blame on you. But also likewise, for like how APTs operate, they also don't want to leak artifacts on target machines, because that's an artifact that could be reverse engineered and analyzed down the line, which is just a leak of your capabilities. We've also got to keep, in fact, network metadata, right? Addresses, host names, IP addresses, also patterns, certain patterns of operations between times and dates, which is commonly used for attribution, right? If you're seeing heavy C2 comms between certain times and dates, you can correlate that to places in the world and things like that. You've also got metadata of the implants themselves, like compile times and dates, what compiler was used, any leaked PDB paths and strings in the binary, the languages used. There's kind of those things as well that we need to keep in mind when designing our code. And these are things that we all consider as we create our code, create our frameworks, create our tools. In terms of logging and things like that, we want to make sure we have the capabilities to do all this for the main two scenarios we identified at the start. One is integration to existing frameworks. A lot of existing frameworks like Cobalt Strike have the capability to track logs. So if we have logging capabilities in our individual tools and modules, we can integrate that with the logging used by, Cobalt Strike or whatnot. Likewise, if we have our own framework, we can use our own framework to extract the logging and things like that from our modules as well. Certain case studies, I'm not going to dive too deep into actual reports here, but just kind of point out some of the notable techniques from myself reading these reports, right? We have things like UEFI bootkits, which also use leaked malicious EFI modules. And in this case, they used ones from Hacking Team's Vector EDK malicious module. So they kind of just repurposed existing malware themselves, which is a legitimate method, right? Not everything needs to be implemented custom yourself. You can repurpose existing malicious tools, which we will touch on a bit as well, but we will focus a lot on custom implementation. We also have like kernel rootkits here. I say legitimate or otherwise because there are kernel drivers that pretty much have rootkit-like functionality, but are actually signed and supposed to be legitimate. They just do really bad things they shouldn't, that can be abused by threat actors. You've also got multi-stage implants. which is pretty much how we're going to operate as well, being modular as possible. And they also use registry for persistent comms, which is pretty neat. Their C2, they encrypt a lot of the key strings like URLs. They also rotate URLs for each implant. They do some cool things like resetting timestamps of files, clearing the event logs. They use obfuscation in some of their malware, which was actually an evolution. Their initial code did not use obfuscation. Their later code did implement obfuscation. So some of these things we'll be implementing ourselves. Like obfuscation, we're going to use ourselves instead of, writing it obfuscated and then doing it later. And they use encrypted comms, and all these are pretty neat features extracted from just public reports on these APTs. And reading some of these things, we note that they're pretty useful. And so these are the things that we're going to implement ourselves. Now, in this case, I don't actually care how they were implemented in APT 28. All I care about is being aware of these things that they do, so that they give us ideas on, hey, rotating URLs for each implant sounds pretty cool. I'm going to do that myself because there has this certain benefits to it. And based on those benefits, it's worth the amount of dev time to implement that in our implants. That's a design decision that we will look at more thoroughly when we work on our implant, and we will actually implement ourselves. With something like Cobalt Strike, some cool things it has is like beacon object loader, right? Being able to load COF files. COF files, they're just another executable format, really. Like ELF and P. It's just an object format. There's certain properties that can differ between formats like ELF and COF, of course, including size and other certain aspects of it. And we'll look into exactly why COF files are used in or manually loaded by some of these tools like Cobalt Strike. And we'll examine the pros of it and whether it's worth implementing ourselves based on the pros of that. Hint, or I guess spoiler, in our case, yes, we will be writing our own COF loader from scratch in Rust as well, because we'll identify the benefits are worth us implementing. Cobalt Strike also has strong logging, which is very nice, and we'll be leveraging that ourselves. Customizable techniques, default loaders that are also extensible with custom loaders to replace defaults, and decent documentation usabilities housed too. These are some of the interesting points that I can pick from Cobalt Strike that we will also be leveraging ourselves in our own frameworks, based on the benefits to them. In creating our own components, there's a few things that we will definitely be keeping, that we'll definitely be doing, I guess, in our implant design. Things like making it modular and extensible, so that it essentially works like plugins. There's a few benefits to this. One is your implants don't all have to use or be compiled with all the functionality, from the start, right? You compile it with the functionality it needs at the core, and then you can, at runtime even load and unload plugins as required. We want low-level and high-level development to be easy, which is partly why we're using Rust, because it's easy to mix high-level concepts with low-level interactions, including things like raw assembly even. We want our code to be obfuscated or to be capable of obfuscation, to be configurable, different formats, P32, 32+, COF, ELF, even custom formats if you like. Potentially multi-arc and platform. Most of our code is x86, 64, and on Windows, but some of it won't need to be tied to an architecture or won't need to be tied to a platform, or both, such that we'll have code that can run on ARM, that can run on Mac, or that can run on any x86 or any ARM64 platform. We want it to be memory safe where possible, which is why also we'll be using Rust, not just for some of the other benefits it gets us in development, but also for its safety features. And, auto-generated documentation from comments and tags, which is in Rust, which is quite handy as well. On the server or C2 side of things, we will be using, like I said, we are creating our framework from scratch as well, which means we will have our own server component to our C2. and we will make it actually GUI compatible, and we will be writing our own GUI. So, a lot of C2 frameworks love the command line, and the command line is cool. I agree. However, I want a GUI. I'm not sure about everyone, but I definitely love working with a GUI, not just a command line. Now, our C2 and that is going to be compatible with both, and we're going to implement both. It's pretty straightforward in the sense that the C2 just needs to have a set of well-defined APIs. And then whether you're writing a GUI app or a command line app, it's just working with the same underlying APIs. The only difference is how it presents it, if it presents it in a GUI or on the command line, right? But the underlying functionality via the APIs are the same. We're going to use encryption with rotating keys, multiple communication channels, implant verification and authentication to kind of be able to identify when implants are being run in sandboxes or again by analysts and things like that. Detailed logging is a must. Report generation is a nice thing to have that we'll explore as well. And part of logging is, artifact tracking. So these are some of the core things that I could think of to start with that we want in our tooling. There'll be things that'll come up later, I'm sure, as we dive more into other code or as you as students point out some interesting, cool things you may have seen that I have not mentioned yet. And we'll go through that as well. But to start with, we have a pretty decent list of behaviors and capabilities we're going to implement to start with in our tooling. Rust, again, language of choice for multiple reasons, including its support for testing and its kind of fun anti-analysis properties, which is pretty cool. And for learning Rust, there's a few things. First of all, I highly recommend, if I just search learning Rust, there should be the Rustlang, official website for getting started with Rust. Now, I highly recommend, if you haven't done Rust yet, follow this. Read the Rustlang book. The book, you don't have to actually read it all. You can click on the key points to it, or you can use this as a reference. If you want to learn about error handling, jump to the error handling section and start diving into some of it. You can do that kind of as it comes up. You can also jump into the Rustlings course, which is pretty nice because it's pretty much Rust by example, right? You get to actually work with it in your own environment and follow along an actual course to learn Rust. Likewise, you can also check out Rust by example. This is very useful if you're also, very strong coding in something else like C. You just need to see how certain things are implemented by Rust that may compare with what you're familiar with. They're the different resources that can be available to you to kind of get a head start into Rust and be aware of the documentation. Cargo book and Rustdoc book are very useful. Yeah. What else is here? The Nomicon is a very good reference. What else is there? Yeah. So this is just very good references for certain things. That said, a lot of the initial code that we work on, actually a lot of the code that we work on will be kind of split into a challenge where I may give some intro to it and then let you explore it yourself, and then followed by a walkthrough. So you'll see me actually coding in real time the answers. So for some things, I'll code it partially and then give the remaining solution. For some of it, I'll actually code through it from start to end in a walkthrough video so that you can kind of learn Rust via walking through it with myself as well, with the projects that we'll be working on. And as we kind of work through that and you work through the Rust examples and the learnings on the official Rust website, bit by bit, you'll grasp it more and more. Now we're kind of starting with implant development, which will be the focus of the next section quickly, and primarily our initial stage, which is defining our development and testing environment. This is key because we want to prevent leaks of our code. We want to be able to have a dev environment where we can test functionality quickly, test detections, but also not risk leaking our code to AVs in the cloud and things like that. Once we have that defined, we'll be creating our initial starting set of libraries. These are common techniques that we must have in our implant. Things like process injection, custom PE and COF loaders, certain things for lateral movement, and also custom packing and unpacking. These are the core features that we'll have in our implant. Before we get to developing them, I'll go through the why and then the design of it, and then we'll jump into the coding of it. Okay, so that's kind of the end of this introductory segment. Next, we'll be going through defining our development and testing environment, making sure we have Rust installed how we want it to be, make sure we have everything set up so that we can code things and test things and not risk leaking our code while we're still developing it. And then we'll move on to the tasks that we want to handle initially, like process injection. We'll go through why we need these core things. We'll go through the design of them, how we're going to implement it based on the different methods available. And then we'll jump into coding it.